right, welcome back to the second talk of the morning session. It's my great pleasure to introduce Axel Kleinschmidt from the Max Planck Institute for Gravitational Physics in Potsdam, who will talk about automorphic representations in string amplitude.
Well, thank you very much, Saul, and thanks to all the organizers for the invitation to this very interesting conference with a very broad theme. So I will report on some work with the collaborators you can see here: Guillaume Bossard, Philip Bleich, Saul Friedberg, Dimya Gurevich, Henry Gustafsson, Daniel Perscher, Boris Puling, and Siddhartha Sai. So that's a long list, and I will draw pieces from the different papers or partly ongoing work that I've done together with them. So this work is about automorphic representations in string theory. And let me start by giving you already the main message, or let's say the main three messages. I'm not sure whether they're all new, but I mean, it seems to indicate they're new. So the first message is that there's a very natural occurrence of automorphic representations in string scattering amplitudes that I will try to explain. So I will say this, and then why is it important to realize this? Because then we can talk about where's the physical information contained in these objects. They come from the Fourier expansion, so the Fourier coefficients of the automorphic forms that make up this automorphic representation, they carry interesting physical structure related to black holes, instantons, and so on. So I will try to give you some taste of that. And the last point, which is maybe interesting for the audience here, is that also the string theory viewpoint that I will try to advocate actually gives you some new types of automorphic representations that I think have not been really discussed in the mathematics literature. So there are many contributors over the last 20 or so years. I've listed the main people who have influenced my work in particular here. And since this is a mixed audience, what I will try to do is I will try to paint first a big picture, giving you a taste of what this is about, and then come to the more original work or more technical points later on. Okay, so starting in that spirit, first of all, I should say what is a scattering amplitude, and in very broad terms, this is something you have things coming in, things going out, and the scattering amplitude is something that determines the probability for a certain configuration to actually happen in nature. So it's very important for any fundamental physical theory, and the way to get this is to start from some fundamental model, some fundamental interactions, and then you can try to compute the scattering amplitude, and this is one of the main things that you want to know in particle physics or other theories. And the standard textbook approach to this is using so-called Feynman diagrams. This is a perturbative approach, so you assume you have some fundamental interaction. Let's say here you have a 3-point interaction with a certain strength lambda called this coupling constant. And then you draw diagrams using these 3-valent vertices in all possible ways. And there are procedures for getting numbers out of this. And the procedure typically gives you some divergent numbers. You have to do renormalization, regularization, and all these things. So it's a tricky business. But it's something that you can find in any quantum field theory textbook. So this is the thing that we would like to understand and where there will be interesting structures. I'm not going to tell you what the precise procedure is, but I want to tell you what is the object that comes out of it. So there will be something that I call an amplitude here, A, and the way that I've written it, it depends on two different parts. So one thing is that it depends on what I call the kinematic data. So this is the information of the particles or objects that are scattering. Here I've written Ki and epsilon I, so these are meant to be the momenta and polarization of the things going in and coming out. So this is actually the data of the process that you want to describe, and then there is some separate information that enters the amplitude, which I call here the theory data, and that is what describes the physical theory that you're dealing with. So this, for instance, contains the coupling constant, so if you change the strength of this coupling constant, you will get a different number, so it depends on that as well. But there can be other theory data parameters that enter into this thing. The way that I've drawn it, as I said, this is a perturbative expansion, and typically, I think it was already mentioned at this conference, this is an asymptotic series. So this looks like you do a power series expansion in lambda for small lambda, but this is not a convergent series at all. In lambda, it has typically zero radius of convergence. And one way of fixing is by introducing additional terms called non-perturbative terms in this context. For example, the simplest one would be a function of this type, which has 0 Fourier coefficients or Taylor coefficients, I should have said, around lambda equal to 0. So these are extra terms that you have to add to this perturbative picture to get the right answer. And in very few cases, almost in no case, the exact structure of this thing actually is known. So this is a very complicated function depending on many variables, and it's typically intractable to compute it in any physically interesting situation. But this is what a scattering amplitude is in particle physics, and the talk is called Automorphic Representations in String Theory. So let's talk about string theory. String theory replaces these lines that I was drawing by world sheets. So instead of trajectories of particles, you have trajectories of strings, and they're you've seen these pictures before. They're drawn in terms of Riemann surfaces that describe the propagation of strings. And the perturbative expansion I had on the previous slides for particles turns into a genus expansion for string theory. So this is now something called the string coupling constant GS. This is the standard notation, and then the different diagrams are weighted by the genus of the surface. So in particular, if you take an n-point amplitude, so you have n ends of the surface, h loops, so genus h surface. What you have to compute to make sense of this in string theory is a certain integral over all possible world sheets of that genus with n punctures, and you give it a weight of this string coupling constant to the 2h minus 1. So you have to compute certain integrals over these moduli spaces of punctured Riemann surfaces that also Sarah discussed on. So instead of telling you how to do these integrals, let me give you an example of what you obtain this way. So one of the standard examples is you take a genus 0 surface with 4 punctures. So this would be M04. It's called the 4 graviton amplitude. So there are 4 momenta, K1 up to K4, and polarizations describing polarizations of gravitational waves, if you wish, going into this diagram, and then you can use all the machinery of string theory to get the corresponding amplitude. So in this case, for this particular diagram, if you follow these rules, this is the answer that you obtained. Let me unpack that a bit. So here now I've written on the left-hand side the dependence on these kinematic variables only through the so-called Mandelstam invariant. So you take certain combinations of the momenta of the incoming particles, called S, T, and U in Mandelstam language, and the square is sort of a Lorentz invariant square. So this is the way that you encode the kinematic dependence. There is this dependence on the string coupling because it's a genus 0 surface that I mentioned. Gamma is just the usual gamma function, and another important parameter here is the parameter alpha prime, which characterizes the string scale. So this alpha prime is the dimension of its length squared, and this length is the typical length of the string. So the bigger LS is, or alpha prime, the bigger you should think this string is. And then the final thing that I'm hiding and will hide all the time is that the polarization here just gets absorbed into some object. But this is a very concrete and very explicit calculation you can do, and you find this answer for this scattering amplitude. Now, this is an exact function of alpha primed. So you can just do the integral and you get this gamma functions from this integral representation. This is something that you can do for this genus 0 surface. If you try to do it now for genus L or H, I should have written a surface. So for higher genus diagrams, it's not known in any single example how to do that for the physical string theory. So this is not so nice, but what people do is they say, okay, let's not care so much about the fact that we can't do the full integral, so we don't find a closed formula. We just compute the integral in a certain approximation. And the approximation you do is, in this context here, called the low energy approximation. So you take these combinations of the variables you see up here to be small. And that's called low energy approximation because S here is like the energy of the particles that are being scattered in units of alpha prime. So this would be low energies of particles being scattered. called the low energy approximation physically, but I mean, it's just something you can do with a function above. In this low energy approximation, you can also compute these higher loop diagrams, and you get very interesting mathematics out of that. These are called modular graph functions. Kim already mentioned them. And there's a lot of work going in this direction in the last 5 or 10 years, because they compute interesting invariants of these moduli spaces of higher genus Riemann surface. So there's many interesting things happening in that direction, but this is not the direction I wish to pursue. So here in the particular case up there, we can do the low energy expansion by just expanding the gamma function. So what we get from expanding the gamma function is what I'm showing here. So you get a leading term, and then you get higher and higher corrections in powers of alpha prime, which measures the energy scale. So you get this so-called alpha prime expansion of the amplitude. And from the gamma functions, you get these interesting zeta values, Riemann zeta at 3 and Riemann zeta at 5. And as I was saying before, this alpha prime parameter is basically the length of the typical length of a string. So if you send alpha prime to 0, then you make a small alpha prime expansion. What you're doing is you're replacing these diagrams by more conventional Feynman diagrams. So that means that there should be an interpretation of this expansion that I've written here in terms of field theory, standard quantum field theory, and there is. The first term here is exactly the term you would compute using Einstein's theory of general relativity. The next terms, they are corrections to this, and they come from the fact that, I mean, we started with the string theory and not with Einstein's theory. So these are corrections to Einstein's general relativity that are induced by, in this case, massive string states. So you generate sort of an effective description of something that modifies Einstein's theory using this procedure. Okay, good. So this gives you some idea, maybe, what this scattering amplitude is about. And here I'm summarizing the same information in a different diagram. Namely, I'm using what is called the double expansion of this string scattering amplitude. So one thing that I was explaining is that the string scattering amplitude has an expansion in terms of the genus of the Riemann surface. So this is the perturbative expansion in powers of the string coupling constant. And I also explained to you that in many cases, the only access we have is using a low energy expansion as well. So if I plot this axis here as the energy scale, the alpha prime direction, I can also do an expansion of the amplitude in that direction. Of course, we would like to understand the full picture here, but often we're only restricted or limited to the part of that. But at a fixed order in this perturbative expansion, let's say for this tree-level diagram, the genus 0 surface, I was showing you how to get these numbers out of this. But you can also slice the same diagram in a different way. You can slice it also in the vertical direction, and this is, you take viewpoint that you want to do the energy expansion and combine all the different perturbative orders together. So if you take this, organize the information of the amplitude in this way, this is where the automorphic will appear. So the surprising thing is that there are some instances where if you go to organize your amplitude in this way, you do the expansion in the energy direction, the alpha prime expansion, there can be discrete symmetries that completely fix what is happening along one of these blocks. This is where the interesting math sits for us here. Good. So what symmetry is it that does this? The symmetry is called U-duality, and let me explain a bit where this comes from. So one thing is that the string coupling constant, GS, is one of the moduli of string theory. And there are other moduli in typical circumstances. They are part of this thing that I call theory data in general. So for example, they contain information about the background in which the string is propagating. To give you an example, suppose you have a torus. So you have a d-1 dimensional torus, just products of circles. Other information that determines the amplitude or that enters the amplitude is, for example, the size of all the radii. So here I've just drawn one radial direction. Let's say the radius is r. in some units. So this will be something on which the amplitude will depend, because depending on how large the circle is, the amplitude for the string scattering process changes. Now, since the string is extended, it's one-dimensional. Here I'm doing closed strings. The string can both wind around the circle, so there's a non-trivial topological winding number that I call W, and it can also rotate around that circle, which I call the momentum n. So these are these two colors here that I've indicated. And something that is not obvious when you see it for the first time, but something that is true, is that there is a duality here. So if you exchange the radius with 1 over the radius, and at the same time exchange the momentum and the winding number, you get something that looks like a very different configuration. But the important point is that from the point of view of the string, this is a completely indistinguishable configuration. So these are fully equivalent string theories. And this is now just a discrete transformation, R going to 1 over R. For the torus in general, you will get a discrete symmetry group, which is just some splits or something. This is SOD minus 1, D minus 1 over the integers. It's related to even self-dual lattices. So this is one part of the duality, of this U-duality. And the other part that is maybe more familiar to people here who work on this Super-Yang-Mills theory is there's also S-duality at play, entering here. Namely, if you take this string coupling constant, it doesn't come on its own. This is in type 2B string theory. It comes together with something called the Ramon axion into a complex variable omega that I've written like this here, which lives on the upper half plane. And in this upper half plane coordinate, you have an action of SL2 Z, which is the symmetry group here, duality group here, which transforms omega in the standard way. And now, something that is for which I can't even draw a picture, but which is nevertheless true, is that also this SL2Z action on this particular combination omega here gives you equivalent string theory. So there's also an S-duality at play here, acting on this upper left plane space. So if you put this S-duality together with the duality I had before, S and T, the next letter in the alphabet is U. So this is what U-duality is. I think U is also for union, but I think it's also really they took it because it's the next letter. What you find is an interesting space on which everything depends. So remember this omega and the radii and so on, I was saying these are parameters, theory data parameters on which the amplitude depends. So now in this very general combined situation, you get now amplitudes that depend on all the moduli of string theory, M, and they're in this locally symmetric space using a split real exceptional symmetry group R, quotiented by, on the one side, the maximal compact subgroup, and on the other side, this discrete Chevalier U-duality. This is really where sort of the arithmetic structure begins for this scattering amplitude, that you have this nice space in which everything lives. Just to put this into a diagram here, so here I've drawn the diagram of this so-called Cramer-Julia sequence of symmetry groups, and E6, E7, and E8 are part of it. And if you make the D smaller than 6, the diagram gives you an idea of what the group is that you get. And this is really combining S and T in this very obvious way. So on the diagram, you can see both the D-type group that I had before and this SL2S duality group. And the fact that they combine in this particular way is not obvious, but true. Okay, so after this long discussion, let's go back to the amplitude.
Sorry,
Yes, please.
can you go back to what is the end? So I guess I didn't care about G.
So this G is a modulus of string theory, so it contains all this theory data. So if you want to compute the scattering process of a string in this toroidal situation, you have to say exactly what the torus looks like. So you have to say how big are the radii, I mean, what are the directions, are the shear parameters. This also contains the string coupling constant and this other parameter. So this really says something about the space on which the strings dynamically evolve and scatter. So this is really part of this thing that I call theory data, that on which the amplitude does depend. And here the statement is that in this particular case, the theory data is actually given by this local symmetric space.
Is it possible to say why a torus? I mean, there are a lot more manifolds available.
Right. Excellent question. So here I'm focusing on the torus case, because in this case you preserve maximal supersymmetry. So there's something in the background that I will come back to in a moment, which is supersymmetry in string theory. And the torus has the advantage that there you can actually preserve all the supersymmetries. Whenever you have supersymmetry, you have very rigid structures, and this is why this becomes so nicely used. But you could try to do it for Halabi-Yau or something like that. People have thought about it, but it's much harder to get structures.
So this is a flat torus. I don't know if it's Riemannian.
It's a flat torus. It's Riemannian. Yes. I mean, this is really just a standard torus. So this the tori here are parameterized by flag manifold SOD, D divided by SOD times SOD, and then there is a discrete symmetry of the lattice that you use for the standard. It carries a metric and a B field. Does that help? Perhaps.
Maybe I could ask a question. So here it's all building on the question what is the little g, but so here there's the initial choice of the torus. Does that maybe I just wanted to understand the inputs, the output is this EDD. I mean, I don't know this kind of EDD. And what was kind of the choice that led to this output? It was the choice of the torus.
So yeah, so this
together with the various symmetries.
Right. So this is really so I was saying there's sort of this thing that I call the kinematic data and the theory data. And this is where this ED symmetry will act. So this is something that I made the choice that I'm looking at the theory where this describes all the possible theory data. So this contains the choice of the shape of the torus, but it also contains the choice of the strength of the coupling constant. So this really fixes what is the sort of physical configuration in which I want to compute this specific scattering process. But here, this contains the choice of the torus is part of this this point that I choose on this one.
Is it physically clear why H should be some kind of end of the world?
Say again, why?
Why D equals H should be a last.
So no, and it's not actually. So you can try to just since I was saying you can take D to be less than 6 here, you can also take it to be larger than 8, and then you get a Kac-Moody generalization of exceptional groups. And you can also study sort of this situation in the Kac-Moody context, and there's some work related to it. So there's one particular case that I will mainly focus on, I think, actually is the D equal to 7 case, because this is the case when you take the compactification of strings to 4 macroscopic dimensions. So this is what the case that is most closely to our real world. But in this thing here, there's nothing particular about 6, 7, or 8. I mean, it's really full.
Does this one go to 11?
Again?
Does this one go to 11?
This goes to 11, yeah. So I think, yeah, so D shouldn't be more than 11. That's correct. Correct.
But you see the exception, sorry. It's a very, like, this is the moment where somehow maybe we have a chance.
Yes.
So the exceptional group is coming, I mean, it looks like I'm just trying to read your cartoon at the bottom.
Yeah.
The exceptional group is coming somehow from a combination of deciding to do the theory on a torus, and then also just keeping track of the dualities.
Right.
So if we understood how those interact, we would see an exception. I mean, that's the
Exactly. So that's where it comes from. So one thing is that, I mean, this picture here, I mean, if you take that part, which I call T duality, which is related to this torus E-1 over there, This is part of the information that you're putting in, and if you were to remove this point here, and take the whole line down here, you have something that looks like an SL group that comes from one dimension higher. So this is sort of an M theory connection.
So why did you circle the whole side for the T duality rather than just the node two?
So because here, so this is really, if I take so this has D minus 1 nodes that I've circled here, right? So this is D minus 1 nodes, and this is really the
Oh,
group.
you're saying the SO, it's an SO or an SL.
So this is this, so this T duality is an SO. And what I was saying before, maybe I didn't say it very well. So if you remove this point here, this is not related to the string torus, but it's related. So here you have an A-type group, clearly. You remove that point. And this A-type group has got to do with an M theory embedding of the string theory construction. So if you know anything about M theory, this might make sense. If not, I'm sorry.
Okay, no, that's good. Great. Thank you.
But this is another way of putting all the different dualities together to see that you get this expression. Are there other questions? So I hope this is not the only point when you ask questions. You want to questions whenever I say something that is utterly confusing. Saying many things that are confusing. Good. So this is now sort of what I've explained to you now is that, I mean, in this particular context here, you have this theory data, there's a relation to exception groups, and there's a relation to some kind of discrete symmetries, dualities, I call. So we want to now go and put this together with amplitudes. So in this particular cartoon that I've drawn here, I've rewritten this alpha primed expansion. So this is an expansion now, again, in this direction there, where I've put the alpha prime dependence into these variables sigma 2 and sigma 3. And this is the only, from the kinematic point of view, these are the only interesting polynomials in this Mandelstam variables st and u that can occur. So you can organize all powers of alpha primed into this expansion here. And then the question is now, what are these functions which now depend on this theory data or moduli G multiplying a specific order in this expansion? So I'm not sure whether you can read this. The first one that I've given here is the first box. It's called 0, 0. So this would have no dependence on these variables. The next one would be 1, 0, which only depends on sigma 2 and so on. So you can really look at the expansion in this way. And the big question is, what are these functions? And these functions, they contain now the non-trivial information about the scattering. They have to be invariant under this discrete U duality. They have to satisfy certain growth conditions because they want to connect to perturbation theory. And what I mean with this is that these functions, they have very complicated dependence on this variable on the group. But if you go to a certain cusp, you should be able to recover exactly the numbers that I gave you before from this these theta values. So they have to have a specific growth condition in order to allow for that. And the supersymmetry that I keep hinting at, they also tells you that you have to satisfy differential equations. So this is exactly what you want for an automorphic form. So this last thing is like Z finiteness conditions. And here I'm actually talking about only spherical objects. So this is now sort of, after this long discussion, a reformulation why automorphic forms come up and how they connect to scattering. Good. Now the question is, now that I've reformulated the problem in this way, what are the specific functions that show up? And for the first few cases, the answers are actually known. So this is, as I said, work that goes back many years by now. For the first term here, which I call 0, 0, there's again this 2 zeta 3 that I showed you, and there's a function that multiplies it, which is just the maximum parabolic Eisenstein series. So here, the notation I'm using is this is a maximum parabolic Eisenstein series associated with this node 1 in the Dünkel diagram. So this defines my parabolic, and it's just some maximum parabolic Eisenstein series for that.
Sorry, before the P and Q, is there a good intuition? I mean, I understand you were trying to capture this expansion in alpha prime powers, but just these two parameter version, is there a meaning sort of separately to what P and Q
No, not really. So the thing is that so P and Q. So I wrote this thing. There's some prefactor, but let's ignore that. S to the n, T to the n, and U to the n. In terms of these Mandelstam variables, and momentum conservation tells you that S plus T plus U is equal to 0. So the only statement that P and Q are making is that you can expand any symmetric polynomials in S, T, and U subject to this condition in sigma 2 and sigma 3. There's no other intrinsic meaning to this. It's just a way of parameterizing the space of symmetric. Good. So yes, so this is just a very simple plain Eisenstein series for this maximal parabolic subgroup.
I'm sorry, I think I sort of understand how you said that you get a group element in spin and n, because that's parameterizing a torus somehow. And I think I understood that the way you get this type E Lie algebra is by adding some symmetries from S duality. I don't understand how you're getting a function on this Lie group of type E. So, I mean, I don't understand where your G is.
Right. So the G really is, so I mean, we started out with, let me go back one slide. So here, I mean, there was something about tori, and the space of tori is parameterized by this symmetric space E type. Then there is S duality, which is the symmetric space of SL2 type. So it's this thing here. And something that I'm not showing here is that there are also the parts of the symmetric space that I haven't shown. So this space here, of course, has a decomposition into the D type symmetric space and the SL2 type symmetric space. And there are what I would call coset components that I'm
sorry. That symmetric. You just said that the symmetric space for this type E group has a decomposition in terms of the spin symmetric space and the SL2 symmetric space?
Well, there's the spin symmetric space sits inside here. That is the way that I think.
But just in terms of making up the dimension, aren't there, in addition to having Riemannian torus, there's also some form fields?
Right. So this is, as I say, so there are some parts here that I'm not showing. So there are extra. I mean, this space here and the dimension of that space is larger than the dimension of the SO symmetric space plus the SL2 symmetric space. There are extra fields that I'm not showing. All fields. So, I mean, to say this differently, I'm not sure whether this will come into. So there, to describe the scattering of the string, I have to give you quite a bit of information. So I have to tell you what is the shape of the torus. I have to tell you what is the strength of the string coupling constant. I have to tell you something about the value of this thing that I call the Ramond axiom. But then I also have to tell you something about other fields that are not shown on these slides. These other fields are the other fields that make up this symmetric space. I mean, there's interpretation for them in terms of form fields and string theory, but yeah, maybe I'm just asking you to take my word. I mean, if you take all the information that you need to fully describe the string background in this context here together, you will get this.
Yes, sorry, it's like a great opportunity. So sorry. So this is an example of a locally symmetric space.
Sure.
Okay, so is that structure something you kind of knew a priori? I mean, I don't know, just far enough away you knew that everything you were going to assemble, I mean, you imagined you assembled it and you got some crazy modular space. New structure. Yeah, what structure? So getting the particulars of this example or this E and so on, just is a locally symmetric structure. Yeah.
So in this case, you knew that you had to get a locally symmetric space, and again, it's related to having maximal supersymmetry. So if you reduce the number of supersymmetries, then typically you will not get maximally symmetric spaces. I mean, there are still, I mean, we mentioned Calabi-Yau before, so you know when you do Calabi-Yau, this modular space will be like a quantum Kähler space with certain discrete symmetries acting on them, but it's not always a locally symmetric. It really depends on
once you have some super.
But in this case here, once you have maximal supersymmetry.
So us finding this was kind of, once you told us that, us finding this was kind of or discrete task.
Yeah. But yeah. But I still wanted to explain roughly.
Of course, yeah. No, it's fantastic, thank you.
Okay. So yes, so we were here. So in this particular, for the first two terms in this expansion that I mentioned in the vertical, so horizontal direction, you get these maximal parabolic Eisenstein series. At this point, the next one I will come to hopefully at the end. Now the question is, I mean, so this is something that you can just fix from all the information that I've given you, which is not actually how it was done historically, but you can do it that way. To check just quickly the consistency with these lowest order results, you can take these functions here and look at their Fourier expansions. Look at the constant term, and particularly just take the identity coset for fun. You get exactly of course, the values that I had before. So this is just consistency with what I said. Good. The title also contains automorphic representation, so let me talk about that. And now this is where most of you will be more.
Sorry, can you what was an Eisenstein series from your point of view? So you got to an Eisenstein series. What was it? It was a scattering.
So the Eisenstein series here occurs in this here. So this is the scattering amplitude in this alpha primed expansion, and the Eisenstein series is a particular term in this alpha primed expansion.
Thanks. That's what you emphasize.
Yeah.
Thanks.
So you sort of separate out this moduli dependence and the kinematic dependence in terms of the sigma variables, and then it's just this piece of the sigma. All right. Yeah, automorphic representations. Let's be quick here. So you take an automorphic form, eta, let's say one of the Eisenstein series, you have the right regular action, you build up a representation space. If we like to do this adelically, at the Archimedean place, you get some GK module, and I'm saying this because I will have some comments on that in a moment. And this really builds up an interesting representation space. So you can rephrase many things about representation theory in this automorphic language. The question that I really want to say is that I told you there are specific automorphic forms coming out of string theory. Is there anything special about the representations you get on the string? This is the point of the talk. And we know Eisenstein series in general. I mean, this is the work of Langlands, of course. They're related to spherical vectors and principal series representations, but I've given you very specific Eisenstein series, so there's something specific for the string theory cases. The answer, of course, is yes, otherwise I wouldn't be standing. Good. So what is special about these things? And in order to say this, I have to talk a bit more about how to do Fourier expansion, and this will be also very familiar to many of you. In the simplest case, if I take just the group SL2R, so this is what I call E1, the exceptional group of rank 1, it's SL2R. This is the Eisenstein series, the first one of the list that I gave you. It's just a non-holomorphic Eisenstein series. You can do the Fourier expansion, you get two constant terms. And then you get, normally you write it as a K-Bessel function, but here I've done the asymptotic expansion of the K-Bessel function. And I've done this in order to show you the physics of this. So the constant terms, they have an interpretation in terms of this perturbative string calculation. So the first term would be 0 loop, and then or tree level, and the next term would be 1 loop. The fact that there are no more than two constant terms for SL2 Eisenstein series actually implies a non-renormalization theorem in physics, which you can check independently, and everything is consistent. The non-zero Fourier modes here, from what I've written here from the asymptotic expansion, you will recognize these are terms which are, in terms of the expansion in GS around 0, are non-analytic. So these are really these non-perturbative corrections that you get from this duality symmetry. So this is imposing duality symmetry using the Eisenstein series, you get information that is beyond perturbation. So this is something that is really impressive from a physicist's point of view. So these are called instantons in this case. Good. So this is the story for SL2, and this also this divisor some sigma. This was checked independently using matrix models and so on. So this is all a very beautiful story. It's getting much more interesting if you go to higher rank. So if you go away from E1, you go to E2. E 3, 4, 5. E6, 7, E8 maybe. So this is where the story gets much more interesting. Now, what does the Fourier expansion do for a higher rank group? This is again something not very surprising. You take some unipotent subgroup of your bigger group. You should have written U of A and G of A here. You define this period integral using a unitary character. It's periodic. Eta is the automorphic form. So this is what I would call a Fourier coefficient. And again, this is not something surprising. This unipotent character, unitary character, you can parameterize also in terms of some nilpotent element of the dual of the lead algebra. Just this is, you can write this as a pairing between the group and the dual, and then you can characterize all possible characters using these nilpotent elements. Now the question is, as you vary this character psi of u, and then keeping this u to remind ourselves that this is a specific choice of unipotent subgroup that I have here. When you vary psi of u, you can ask, when is this integral 0? When is it non-zero? What do you get? And the thing that my understanding of wavefront set is that the wavefront set of this particular automorphic form eta, or of the automorphic representation even, is just the collection of the nilpotent elements for which the Fourier integral is non-zero. Objections to that? Good. So then this is really typically something that organizes really into nilpotent orbits here under the group action. So this is something that characterizes eta. This has been discussed in several places, both locally and globally. These papers here in the pamphlets. So now the question is, so this is, we have this notion of wavefront set that characterizes, going back to the particular string theory automorphic forms, is there something special about the wavefront sets of these functions? And if you do the calculation, these specific automorphic forms you have here, because there's again supersymmetry at play, which I've written here as BPS protection. This means that most of these Fourier coefficients for choices of psi of u actually vanish. And more specifically, if you take the first function that you get in this alpha primed expansion, the only non-zero Fourier coefficients arise when this character psi u is associated with a minimal nilpotent. If you go to the next function, E10, this has non-zero Fourier coefficients only if you're in the closure of the next to minimal orbit. So I've written them in terms of Balak-Hart terms here, 1 and 2. So this is very nice. And I mean, you asked before about P and Q. I mean, maybe a better way of doing that is giving them different names. So here I call them minimal and next to minimal. And this is telling you that really string theory and this alpha primed expansion gives you instances of so-called small representations. These are typically very isolated and very special automorphic representations, and somewhat surprising, I would say, at first, but also nice that exactly these special examples are the ones that come out of the string theory calculation.
When you're talking about the symmetry in this setting, is there, do you mean that like each theory for each G has supersymmetry, or the supersymmetry acts on the whole family of
So for any value of this so G is here, for any value of this G, you have supersymmetry.
yeah, then maybe it's so early to ask this, but how do we get differential equation if it's acting each G?
So the way to get the differential equations is that it's a bit roundabout. So you write down. It's actually something that I didn't say, but I wrote on the slide. Let's go to the slide. So these terms here, because they're alpha primed expansions from the point of view of field theory, they have an interpretation in terms of higher derivative equations. So this R to the 4 is short for Riemann tensor to the 4th power. So this is a higher curvature Hermit has more derivatives. Normally field theories have 2 derivatives, but this is 8 derivatives in total. So you write down a theory which has 8 derivatives and which contains this function. And if you demand this theory with 8 derivatives to be supersymmetric, then the coefficient function that appears in this theory has to satisfy differential equations. So the supersymmetry does act on G, but for any value of G, you want it to be supersymmetric, and this is where the differential equation with respect to G comes from. So you really make so it seems that you're not really transparent. So you write some action S, you write this in terms of some S0, and then there will be a term alpha primed, let's say cubed. So this would be R and then cubed. This would be R to the 4th. You know you want to also define a supersymmetry, which will be so has an expansion in the same alpha prime parameter. So if you impose that this action that you're writing up there should be supersymmetrically invariant, there will be a cross-talk between acting with this supersymmetry on this particular term and with this supersymmetry on this particular term, and imposing now that they cancel, this gives you the differential equations that act on G. Of course, I should have written plus dot. This is this goes on. Okay. This we've said. So we have these small automorphic representations. Now, maybe just to say one short thing. So from a physics perspective, what particular types of Fourier coefficients are we interested in? So there, for these higher rank groups, of course, there are many choices of unipotents, and the ones that are of most interest in many examples are those coming from maximal parabolic subgroups. And there are 3 preferred choices for these E-type groups. So one is this thing that makes the T-duality more manifest, and there's the one. So this is the one when you take the diagram and you move first node 1 of the E-type diagram. This is when you remove the exceptional node at the top, and this is when you embed ED minus 1 in ED. So these are all maximal, these are the Levy's, maximal parabolics, and they have interesting physical interpretations. So the first one is related to string perturbation theory. So what you will see in this context are instanton corrections of the type that I mentioned. This one here, as I say, has a connection to M theory, and there are so-called M instantons that come up here. And one thing that is also quite interesting, that's not the way you normally think about Eisenstein series, but this connects to certain black hole counting problems. So there's different physical interpretations of these different choices of maximal parabolic subgroups. So, and because they have this interesting physical interpretation, we're typically not only interested in saying which Fourier coefficients are 0 and which ones are not 0, we also actually want to know what values they have. So we want to explicitly compute the Fourier coefficients. And this is, yes, please.
So for Borel's, Eisenstein series already appeared, and then you jumped up to these kind of maximal proper.
There were Eisenstein series for maximal proper parabolic already, not the Borel.
That's right.
The Eisenstein series. Those were. So here, this is kind of explaining the physics behind which Eisenstein series you were.
No, so there are 2 different parabolics at play here. So one parabolic, maximal parabolic, I was using to define these functions. EPQ. They were like a maximal parabolic Eisenstein. I would call that. We call that parabolic Q. This is just something for it was P1, let's say. Great. So this was a specific maximum parabolic of inside ED. And then, of course, you can take now this maximum parabolic Eisenstein series here and choose a different parabolic for the Fourier expansion. So this is what I'm describing on this slide here.
Oh, I see.
So because
P1 on the slide,
say again?
is P1 on the slide?
Yes, so P1 happens to be the first case of this. So you, of course, you can expand it in that same parabolic, but you can also expand it going to different, I mean, this is going to different paths on the symmetric space, and they have different physical advantages.
So we're very far. Like.
Very far from the brain. And which is related to the fact that these are small representations. So these are, first of all, the degenerate principal series, and there are very specific points inside the degenerate principal series where you have even a further reduction of the delta period of dimension to small. It's very far from the generic case, as far as possible.
And then you'll be taking residues to get the small.
Exactly. So you could take residues of here. So you go to the specific places in the degenerate principal series using residues. Where
Yeah, so you would arrive, you arrive at a Borel by doing an iterative story of what you're, is that?
like you know, so actually none of the things that I was saying there was a Borel.
No, I understand. I guess I just wanted to know if the Borel appears for you at all, if it like appears as the result of doing so.
You could take a multi-residue if you start from the root to get the sneeze working.
Oh, I see.
Right.
Thank you.
Okay, so thank you. Good. So, but now there's a Borel.
This is why I asked.
Yeah, exactly.
I realized I was confused.
This was not planned by me. So the thing is that, so on the previous slide, I described certain choices of unipotent glue where we are physically interested in computing the Fourier coefficients and we want to make it more. But this is actually something that for which not so much literature was available. You have much more literature for the Borel case. So if you take an automorphic from eta and you compute a coefficient with respect to the maximal unipotent, which I call n here, and these I will call Whittaker coefficients. So this is the standard Whittaker integral. So there's a lot more information about these Whittaker coefficients. And one of the things that you can wonder is, can you use the information that is available for these Whittaker coefficients to compute these more general degree? Is there a relation between the two? So let me remind you what is known about these Whittaker coefficients. So one thing is that if you take a generic principal series element eta and the generic character here, this integral is known to factorize. You have the Kasselmann-Schaleika formula for the p-adic places. And actually, if you take one of these degenerate cases where the Eisenstein series eta is like a residue of one of the minimal Borels, minimal Eisenstein series, you can find some kind of reduction formula that computes this Whittaker coefficient. Then eta is not generic. It's no longer Eulerian, but you can still compute it using some kind of reduction. So this is information that is available. And so there's a reduction formula that you get for these W's. And now in this work that I'm not going to discuss, we have worked out how to use this information for this Whittaker coefficient W to compute the Fourier coefficients F. So this is this work with Dima Gurovic, Henry Gustafsson, Daniel Perschon, and Siddhartha Sahi, where we really showed how to do we have a procedure for computing the F in terms of W's.
I thought all these Whittaker coefficients were zero for your automorphic forms.
No, they're zero for generic psi. But if I take so psi is related to which nilpotent element I take. If I take a representative of the minimal thing, which is only supported on a single simple root, then
that's the only one that's called Whittaker.
Right. So here I'm using it slightly more generally. Then so Whittaker. There are also these degenerate Whittaker models that have been studied. Here, this is for me also Whittaker. It's a degenerate. Sorry for misusing. So I wanted to jump to this place. So the last of the three messages was, is there anything interesting maybe coming out of string theory for people interested in automatic forms? And again, this diagram that I've shown a number of times now, you do the alpha primed expansion. I've shown you the first two terms here are the minimal Actually, I didn't say the very first one is the trivial representation. The minimal, the next to minimal. Maybe this is something you want to continue in that direction. On the right-hand side, I've shown you the corresponding Hassel diagram for the nilpotent orbits in the case of E7. We start with the minimal next to, trivial minimal next to minimal. For E7 here, you come to a branching point. You can ask yourself, what is the correct representation that you get here? So why not? If you do the calculation, you can, from supersymmetry again, you can look at the differential equations, which give you some information about the annihilator ideal. So the differential equations here, if you analyze them, tell you that the corresponding orbits you expect actually have two maximal elements. This is something that normally you don't expect for automorphic representations. You want to have a unique maximal element wavefront set. What I'm telling you here is that this thing, if you analyze it coming from the physics and the supersymmetry, you will find two maximal orbits, maybe this one here and this one up there, in the wavefront. There, I mean, this is really something we know from physics has to happen in this case. Okay, and the reason is that the differential equations now have this driving term that Kim already told us about on Monday. So instead of having an eigenfunction of the invariant differential operators, you have a source term. You have a driving term in the differential equation. And this takes you outside of the world of usual automorphic forms. So you no longer have to deal with GK modules. We have a slightly more general structure because of this forcing term. And you can really ask yourself now, what are the functions that satisfy this more interesting differential equations? There are different methods for analyzing this detail. We have specific solutions for all these E-type cases. They look sufficiently scary. There can be some kind of generalized theta lifts using genus 2 invariants, whatever. So they're sufficiently scary. And one of the points is that we only have partial information of the Fourier expansion in that case. But the point that I really want to get across here, and this is what I will end with, is that these functions, they are not Z-finite. They're really not standard automorphic. And this is the thing that together with Sol and Guillaume Bassat and Margurovich and Daniel Persson, we're analyzing at the moment to really find a nice mathematical language for describing these things. So more generally, instead of having GK modules, we will have U of G modules. So you still have an action of the differential operators, you have differential equations. You have these inhomogeneous differential equations. What we are finding as a picture is that you can fit this structure of the differential equation into some kind of exact sequence of these modules, where you have as an auxiliary object a specific parabolic Eisenstein series. And this exact sequence, when you define it properly and you make it descend to the Fourier coefficients, you get very interesting consequences, for example, related to exponentially growing Fourier coefficients, which you expect physically again from black hole counting, but normally you don't have exponential growth in Fourier coefficients. But here, physically you expect that, and you can actually, so we have indications that this also comes out of mathematical theory associated with this differential. So this is really work in progress that is very exciting, and I think it's at least widening my horizon. This is maybe the last point of the 3 bullets that I wanted to get across. There are many things to deal with here, to explore.